program, I'm working with my mentor Isaac and Professor Gordon's lab on a project called Preparation and Characterization of Optically Active Metal Probes for Scanning Chemical Microscopy. So you may have heard about nanoscience and nanotechnology, but how did science get here? Well, innovations in imaging tools allow scientists to see at the nanoscale and do things such as catalysis, nanosphere lithography, nanoparticle synthesis, and nanorods, which are shown here. So how do we see at the nanoscale? Well, let's say we're trying to look at the tip right here. We could use light microscopy, but once we get down to about a micron, it starts to get blurry, and this is called the diffraction limit of light, and we can't see any further. So we could use electron microscopy. This is a black and white picture of electron microscopy that you've seen before. And it's the same tip, but we could get down a little more. And using that tip, we could also do another technique called scanning for microscopy to scan a sample and get the topography of it. And this measures the tip surface interaction to produce the image. And it's kind of like dragging a needle across the surface to give you the height of the image. But neither electron microscopy or scanning for microscopy give you the chemistry, which is very important on the nanoscale. So there's a new technique called tip-enhanced Raman spectroscopy, or TERS, that combines the chemical information from light microscopy with resolution of scanning for microscopy, and this works like this. So you shine a laser light onto a surface, and when that happens, most of the light, almost all of it, gets reflected back in the same color, but a small portion of the light gets reflected back in a different color. This change in color, or energy, is due to the absorption in the molecular vibrations, or you're paying for the exciting the molecular vibrations by changing in the color with the photons. But this effect is still on the macro scale, and you can't see small details on the surface like this. So what we do is we bring a metal tip down to the surface, and that metal tip has electrons in it, and when the photons in the laser hits the metal tip, it is coupled to the metal tip and produces an enhanced field at the apex. And this enhanced field enhances the Raman scattering, which I said before is the change in color. And that allows us to produce a chemical image at the nanoscale. So critical to this technique is the tip that we're using. So we could bring a tip down to the surface and follow the contour. But when we have a big tip like this and try to follow this contour, it's going to be hard, and we're going to get a smeared out image like this. So we want a tip that's sharp like this, so we get a nice image. But the problem is that it's hard to make these sharp and optically active tips. So a project in the broader sense is to make more of this sharp tips, but it's very hard to do. And how we make these tips is by a process called electrochemical etching. And we set up the electrochemical setup right here with the electrolyte, and I'm showing you how to etch tungsten right now. Electrolyte being the potassium hydroxide, and the wire being the tungsten wire. And once we put a voltage across it, current flows from the wire to the color electrode, and that oxidizes the wire. And the etching happens preferentially at the meniscus. And when the bottom half of the wire drops off, you get a tip that looks like this, or a dull tip that looks like this. But even when we use the same conditions and try to reproduce the sharp tip, it's very hard to do. So it needs a lot of feedback to tell us how it's going. And this paradigm is called cook and look, because you just make the tip and see with a microscope. So we really need feedback to make better tips. And here's one type of feedback. We're looking at the current graph as shown before, and this is just the current as a function of time. And at the end, you see that when the current drops to 0, that's when the etching is complete. But you see that even though these two current graphs are very similar, you get very different tips. So this is not a good feedback. So we want feedback on mass changes as the tip is etching, surface area changes, and we want to also have feedback for etching dynamics and hydrodynamic effects, such as the one shown here. We have the vortex going on, bump flow, bubbles, electrolyte ions attacking the wire, and wire ions dissolving out. And we want to see all this. And how we're going to do that is by using a quartz tuning fork, which is a very small piece of electronic equipment that is found in quartz watches as a frequency standard. And this quartz tuning fork is very sensitive to the environment. And the idea is that we want to use this tuning fork and we're going to attach a wire to it so we could detect these changes. And here's an equation that describes the motion of the tuning fork. You might remember this is a damped harmonic oscillator equation. And by looking at different variables here, for some it's like mass and force, we could see what's going on with the tuning fork and ultimately the wire. So we're going to use the tuning fork resonance to follow what happens during tip etching. And the big idea is that we're going to combine the two control loops, one being the tuning fork and the other being the etching, at the same time, and analyze oscillation and current versus time, and connect the oscillation changes in the tuning fork to tip etching dynamics. So I'm going to tell you about the experiments I did to see if the tuning fork is sensitive to the environment. And again, we're going to be looking at the different variables here. Key resonance parameters being omega naught being the resonance frequency, which is right here. A being the amplitude or the peak of the curve, and Q being the general shape of the curve. And as you see here, it's very different in air, water, and oil. And first, I'm going to tell you about the frequency. So if you imagine a musical tuning fork, and you strike it and it makes a sound, and as it's making the sound, you dip it into water, it's going to produce a different sound. This is just the same effect. As you increase the immersion from 0 being no immersion to increasing immersion with x-axis, the resonance frequency drops. And it's linear for both water and oil, with oil being a higher drop because oil has a higher viscosity than water. And this relationship is shown here. As immersion increases, the effective mass increases due to the increased area and immersion interacting with the fluid, and the frequency goes down. And this agrees well with our theory. So the second thing we looked at is amplitude. And the amplitude drops in both water and oil because as the immersion increases, the area also increases, area of immersion increases, and this increases the drag here, with area being right here, and it decreases the amplitude. And yes, this also agrees with our expectations, and this is good. And lastly, I looked at the Q factor. Again, the Q factor measures the shape of the curve, and in physical, it measures the viscous dissipation. And you see that the shape of the curve is very different for water and oil. And when we saw that as the viscosity of the fluid increases, or oil has a higher viscosity than water again, and that really changes the Q. So this also shows that we could use the tuning fork to probe viscous dissipation. So in summary, I developed a tuning fork analysis system to investigate tip etching, and I used that system to do some testing about what will happen during etching, and we saw that the tuning fork resonance frequency, amplitude, and Q reveals the local wire environment, and therefore, the tuning fork is a promising approach to learn more about the etching process. In the future studies, I'm going to actually use the tuning fork to diagnose the tip etching and perform a more quantitative study using a fork and wire oscillations and mass transfer and chemical reaction during etching using chemical engineering principles. And lastly, I want to give thanks to Professor Gordon and the Gordon Lab, and my mentor Isaac for teaching guidance and inspiration, Erica for support, Youth Leads program, and the Department of Chemical Engineering. Thank you.
Questions for Jae? So Jae, so it sounds like you've got some promising results. How far off do you think you are from actually being able to use the tuning fork to guide your etching of each tip?
Well, at the moment, I'm currently rebuilding the thing to be more stable to outside oscillations and noise. And once I do that, it'll be almost immediate that I'll be working with the etching and using the tuning fork as a diagnostic tool. So it's not very far away. Yes?
So can you go back to the slide where you had the size of your tip kind of is going to dictate the resolution of your surface? Yeah. So what would be, what is the resolution that you guys are seeking to get? How far off are we from that resolution currently?
Well, if you have a sharp tip every time, then it's going to be easy to get a good resolution. but it's not that easy to get those sharp tips. And with the sharp tip, you could get resolution down to like nanometer scales.
And so is it a twofold problem that we want A, sharp tips to get nanometer scale, but B, the reproducibility is difficult?
Yes. Well, it's really one thing because you really want the sharp tips, but it's hard to make it. Yes.
So once you, oops, go ahead first. So once you have the tuning fork working, what are some things you can change in the acid bath to make a good tip?
Well, in the literature, most people are studying the different electrolyte conditions and the voltage, just the setup part. So what kind of setup that we're going to use is already optimized for that. And the tuning fork is really going to tell us like how's the tip going to look after we etch.
Okay.
Yes.
So I saw that you're going through with different frequencies and testing the tuning fork. Do you know what kind of effect would have you change the frequencies from maybe thousands of hertz, maybe tens of hertz, or maybe up to maybe megahertz? If it makes a difference.
So the tuning fork oscillates at a very specific frequency, depending on the environment it's in. And that frequency, as you see it in the resonance curve, let's go back here. This resonance curve, so it only vibrates with a high amplitude at that specific frequency. So even if you excite it at a different frequency, say here, it's not going to be very useful because the resonance frequency is right here.
Any other questions for Jae? Okay, great. Thank you.